left.
Okay, so here's the second part of what we missed. And so here we're going to be in section 6.1. So we're going to start RLC circuits. So RLC circuits, as you might imagine, have an R, an L, and a C. We are going to have a series version and a parallel version. The series version, what are we going to find first?
Voltage.
V sub C.
Mm-hmm.
Yes. And for the parallel version, we're going to find I sub L.
I sub L.
Because those are the things that don't change. So that we carry with us. Then the other thing, though, is that, and so you can think about this too. This is a second order equation. It's a second order differential equation. It's got two storage devices, L and C. They go different ways if you think about it. In the sense that the voltage across the inductor is L di dt, but the voltage across the capacitor is 1 over C times the integral of I. And then R, V sub R is just R times I. So you can see where we're going to get the second order from. Because we have a derivative and an integral, and eventually you could have a derivative and a second derivative. So this is where the second order part comes in. Okay? So we're going to have a different solution, but we're going to do the same sort of thing, which is to say we're going to develop, and I'm not going to do the derivation for you. I'll post something online. You can sort through all the derivation yourself. It's kind of long and it's not particularly instructive. And you're going to do it in differential equations, so I'm going to let Peterson do that for you. But what it turns out that we're going to need to find, some things stay the same. So we still know that V sub C and I sub L cannot change instantly. That doesn't change. So we will need to find those. We're going to need to find V sub C at 0 minus and I sub L at 0 minus, and those will not change, so they're going to give us what we need at 0 plus. But it turns out, based on the equations, we're also going to need to know either I sub C at 0 plus or V sub L at 0 plus, depending on which type of circuit we have. But these can change instantly. So I can't use my initial condition circuit to find that. So we're really going to have kind of three circuits. We're going to have our initial condition circuit. We're going to have our t equals 0 plus, just that tiny slice of time when these have not changed, and so I can find those. And then we're going to have a t greater than 0, and that's going to be our response circuit. So t less than 0, initial, t right at the change, just the instant after the change, and then t greater than 0 is our response circuit. So all we're going to do today is work on these first two pieces. So next class we're going to develop what our response equations look like. So for now, just because we need to spend some time doing this piece. Okay, so let me see what else I need to say. So here are some notes that I recommended telling you guys. When we do this circuit, you may want to draw sort of a dotted line around the capacitor and the inductor, because those are like the temporary sources, you can almost think of them as, right? Because they're going to have some initial value, and then in that single instant, before they begin to change, they are like a source. So if we draw a little dotted circle around it, it kind of reminds us that that's what that is. Please be very careful with current and voltage directions, because we're going to start to be having bigger circuits, and so we need to be careful how we have defined our voltage drop, because the current will be in the direction of the voltage drop. All of our circuit analysis techniques are available. So everything that we did in Unit 1, all of the dividers, mesh, node, everything, these circuits get a little bit more complicated to begin with, so we're going to have a lot more that we'll work with there. And then always find these. We're going to find one of these we'll do them both today, but we'll find one of these depending on what solution we're looking at, whether we're looking at series or parallel. So we'll pick one of those later. Okay, so let's do some problems. Here's problem number 1. Oh, erase. All right, so here is problem number 1. So we have an 18-volt source, 2 ohms, L, they don't give us L. Do we need L for initial conditions? We don't, because it's going to be a short, so we don't actually even use that value, right? It's our response circuit that has the value where we need the L and C values. And so then we have a 5 ohm, a 4 ohm, and a capacitor. So the first thing we're going to draw is what happens, we need to find all the values at 0. So V sub C, V sub L, I sub C, I sub L. We have to find them all. The important thing is, the first thing we need to do is we need to look at our initial condition circuit, which is before the switch opens. So first we'll draw that one. And it's been in place a long time, so I'm going to draw my inductor as a short and my capacitor as an open. And then we'll see what we have left. Okay, so oh, and we do have this one, don't we? Okay, so 2, 5, 4, 18. Okay, so I think that's the circuit that I have. Here's plus minus V sub C, and here's I sub L. Okay, so let's think about which way is the current really flowing in this circuit. It's coming out of the voltage source, going through here, and then where? Up here, right? It's skipping the 5 volts because that's shorted. If I have a choice between 5 and nothing, I go with nothing. And then it comes down here. It doesn't go through here because it's open. So I'm going to disregard that one. And really my current is going kind of like that. So if I want to know I sub L, I've got 18 volts, 6 ohms. So I think I can just do V equals IR. Or if you wanted to, you could do a KVL, minus 18 plus 2I plus 4I, either way.
Is it possible to do the short transformation?
It is. I think that's more work than you need to do.
Okay.
Because right now this is just 18 in parallel, in series with 2 resistors. That's a
Okay.
very, very simple circuit.
Okay.
So I think we're going to stick with the simple circuit and just say that I sub L is just V over R. Right, because the current going through the 2 and the 4 is going through the inductor. So I'm just going to get 18 divided by 6, so 3 amps. So that's 0 minus. V sub C of 0 minus. Again, I just have an 18 volt source in series with a 2 and a 4. The voltage for the capacitor is simply the voltage across the 4 ohm. Right, so here's my here's my voltage. I'm tracking back until I find something I know. It's just the voltage across the 4 ohm resistor. Well, if it's just that's just a simple voltage divider then, because we have 18 in series with 2 and 4. So this will be 4 over 6 times 18, 12 volts.
So assuming if we don't use the voltage division, can we just use ohm law like V equal IR?
Yes, if I already know I, right, and I know I is 3 amps, then 3 times 4 is 12 volts. Yeah, absolutely, sure. Mm-hmm. Yep. Okay, so so now I move to a new page to give myself some space. So now let's look at what happens when I open the switch, because that's going to change things a little bit. And again, remember here, if I'm looking, so I have been asked to find the initial values of all four, V sub C, V sub L, I sub C, I sub L. So I have already found the ones that don't change. That's all I can find from the initial condition circuit. Now I need to draw it with the switch open, so I'm going to pull this out. I'm going to put my inductor and my capacitor back in and draw just a dotted line around it, because in that instant of t equals 0 plus, in that one instant, I know its value. It's going to instantly start changing after that, but for that one instant, I'm going to know its value. So here we have t equals 0 plus. Let's see what we have. We have 18, 2, 5, inductor, capacitor. So 2, 5, 18. And now I'm going to draw this here and this here, because I already know some things. I know that this is 12 volts, and I know that this is 3 amps. Sorry. So in the instant at t equals 0 plus, before these start changing, because they're going to start changing, but in that instant before they do, now I have something that I can solve. Okay, so let's look at what our options are. We are trying to find this current and this voltage. Those are the two things we're trying to find. Okay, so what are our options?
Mesh.
Yeah, mesh.
Node.
And mesh, what do I know about mesh? I have two meshes. One of the currents is known. So I just have one equation. So if I use mesh, I have one known, one unknown, so one equation. If I have node, what am I going to do?
None are actually extraordinary. Well, one
I have
extraordinary.
one here
and one before.
and one here. I have two extraordinary nodes.
Is it supernode?
Not a supernode, because that would be connected by a voltage source. So here I just have two node equations, except that this node is temporarily known. Right? This node right here is 12 volts in this one instant. So again, I would have one known and one to write. A little bit harder to see that one, I think, but same thing. So one is known and one equation. My thought is, if mesh and node are about the same in terms of number of equations, mesh has fewer fractions, so I usually go with mesh in that instance. So let's go with mesh. I'm going to draw on our, so here's, I'm going to call this 1, and then this one up here is 2. So I'm going to go with mesh. So KVL for 1, I should just do 2 first. KVL for 2, I know that I2 is equal to what? It's actually equal to 3, right? It's going in the same direction. So I2 is equal to 3. I'm looking at KVL around mesh 1, minus 18 plus 2I1 plus 5I1 minus I2. And then what do I bring it back down? So I've got minus 18 plus 2I1 plus 2I1 minus I2. What do I do with the capacitor?
That will be just trouble.
This is this, 12 volts, because I'm just in the single instant, and it's a drop, so it's positive. So plus 12 volts. So when you solve that, you're going to get I1 is equal to 3 amps. Okay, so if I1 equals 3 amps, I1 is IC. So I have found one other thing. I was looking for I sub C of 0. They're in the same direction. So I sub C is 3 amps. I sub C at 0 plus is 3 amps. V sub L, what's that? V sub L
5 times I.
It's the
minus
voltage,
I2.
yeah, it's the voltage across the 5 ohm. And so it's going to be I1, which direction will it be? This is equal to this, so it's I1, and I'm dropping in this direction. So I1 minus I2.
Yeah.
Okay, so V 5 ohms, 5, I1 minus I2. They're both 3, 0 volts. So that's just an oddity. It's temporary, it's going to change instantly. It's going to start changing immediately after this. Right, so remember this we do only in the single instant of 0 plus. Because immediately thereafter, the capacitor and the inductor, they start undergoing exponential change. And so this only works for 0 plus. So this is as far as we're getting today. Next time, we'll look at then what do you do when t is greater than 0. Now that I've got all my initial conditions, then I can start moving forward. Okay, so this is all we're doing for today. Oh, except wait, I forgot. We also need what happens at t equals infinity. So at t equals infinity, again, I can look at this. I'm going to redraw this one. Sometimes when we have R and L, we get enough going on that it's a little bit easier to draw some extra circuits. So where is the current flowing? Comes up here, and then, nope, there's no current flowing, there's nothing here. There's no complete circuit here. So we know then that I sub L of infinity is 0. And what about V sub C? If there's no current flowing, 18 volts. If there's no current flowing, that's all it must be. 18 volts. Okay, so again, for today, the important thing that we're doing is we're finding all the initial conditions. Previously for RC, we just wanted voltage. And for RL, we just wanted current. Here, when we get RLC, we're going to need 3 of the 4. And we'll get to that next time. So 2 of them are easy. I sub L and V sub C don't change instantly. So we just go back to our initial condition circuit. And we figure it out just like we have been. There's nothing new there. What's new here is this one. The idea that in the instant at 0 plus, the inductors retreat like a source, like a fixed value. Maybe that's a better way to think of it. This is a fixed value of 3 amps, and this is a fixed value of 12 volts. For that single instant. And so for that single instant, then we can find the other initial values that we need. Then we go to t greater than 0 and start getting equations. Okay, so let's do another one. So here's this one. So again, we just want I sub 1 of 0 going through the inductor and I sub 2 going through the inductor. That's all we need. So maybe I should have done this one first. This one's pretty easy. Well, okay, so in the instant at 0 plus, I'm going to just redraw this circuit with, you don't have to, but I like to, with my inductors as shorts. So I've got 30 volts, 8 ohms, 6, 3, so that's what I have. So let's think about some options. This is a fairly simple circuit, but we do have some options. Any thoughts? We could, I'm just speaking to the crowd, I would say. So there are a couple of things we could do. We could find the voltage here with KCL, right? So we could do one single node equation. We could do 2 mesh equations. That seems overkill. So I'm gonna look at some options. options. I could do node, one equation, and then the currents are easy. Then I just use I equals V over R. So that's one option. I could do mesh. I'm going to have two equations. One of them is I sub 1 is going to be a combination of the two. I sub 2 will just be the single current, so that's not so bad. I could do a source transformation, and then I'd have a current in parallel with 3 resistors, and I could do that pairwise thing, pair one to go with the other, so I could do that. I'm not sure that I'm loving that either. So source transformation. So we have current source in parallel with 3 resistors. So we just have to do them in pairs for current division. I could find the total current. I could collapse these guys. I'm thinking this one I can do in my head. 6 in parallel with 3 is 2. 2 plus 8 is 10. So 3 amps coming up this way. And then 3 amps split, 1 and 2. So I can do that one in my head. Okay, so that's the other one, is to look at total current.
You're basically just doing current division.
What's that?
Would you be doing current division after?
Yeah, exactly. Total current and then current division, but it's so simple I can do it all in my head. So, so let's go ahead and do that one. So if I find the total resistance, that's just 8 plus 6 in parallel with 3. 8 plus 2 is 10. So that means the current coming out of the source is going to be the 30 volts divided by the 10 ohms. The total current being supplied by the source is 30 divided by 10, 3 amps. And now using current division. But again, part of the reason I'm saying I can even do it in my head is because I know this one is twice the resistance of this one, so half the current. Right, so I mean, I've got sort of, so I see 1 and 2. But you can also write them out. So current division, I1 is equal to 3 over 9 times 3 amps. And I sub 2 is 6 over 9. Or you don't even need to do that, right? Which is just 3 minus 1. Okay. So again, multiple different ways to attack a circuit. We need to remember all of those things from Unit 1 we're going to keep using. Every now and then, Thevenin comes up and helps us because it's an easy solution, but then also all of our node, mesh, source transformation, V equals IR, division, all of those things are fair game. Okay, so last one. We might get this on one video. Let's see. Could you do me a favor and see how much time is left? Sure. How much time has gone so far? What's it say?
So 6 minutes, 38 seconds.
Left?
I don't know. 23 minutes, 26 seconds, I
Yes, so I got
suppose?
6 minutes. All right, let's see if we can do it in 6 minutes. Okay. Yeah, no. That's not going to happen in 6 seconds. All right, so.
That's the bottom, the top one.